systems where you can get some real insight into formulation issues. And then tomorrow, David Fairhurst is going to go through some more practical applications, direct applications that you can use in a laboratory or in a process environment. So just to say a few little bits about the machine and the team. There's quite a few of us now in the company, started by myself, Roger Petman and David Fairhurst, and then joined by Keith. And then we have some other industrial expertise who have joined us. Our business expertise is Dr. Roger Petman, and he is the CEO, and he's actually an organic chemist. So we're all scientists of one type or another. And this is really our aim, you know, is to use our combined expertise to solve problems in formulation science. And the main tool we're going to use that is magnetic resonance. And that's why we're here. So the device we have, which I'm going to show you a picture of in a moment, is small, it's non-invasive. You can put anything you can get into a 5mm glass tube, you can make measurements on. Our current machine just looks at protons, but in principle, we can look at any nuclei in the periodic table. And what we see the advantage of this machine is in formulation issues. If you've got a dispersion, for example, that flocculates, you want to find out why, if you want to follow settling, a whole range of different things you can easily look at with this relatively simple experiment. So a bit about NMR history. NMR machines have changed in size over the years. And on the left-hand side, you see one of the first NMR machines built by Varian and Packard. Packard, who then formed, or his family formed Hewlett-Packard later on. You can see how huge it is. And that was a small 60 megahertz NMR machine. In the center is a modern high field NMR machine. And you can see from the chap on the top putting a sample in that this is a major piece of equipment and costs several £1 million. By comparison, and roughly to scale, is the Magnometer, which is on the bottom right-hand corner. So this is a small device. And the heart of it is the little box on the top right-hand corner, which is an ARM processor. It's a very powerful small computer system that generates all the different pulses and sequences and what have you need to do an NMR experiment. So what does NMR measure? Well, it measures where protons are and what they're doing. So for example, this is a picture of me many, many years ago before my hair fell out. And what happens if you take an MRI image of my head? So when your MRI works by just finding out where water is and where water isn't. And so you take a slice, and then each slice has a voxel, and each of those voxels contains a little NMR signal that we can interpret. Now, our current machine will do one-dimensional imaging on very small objects, but our main thrust today is to use relaxation to measure NMR. And that was a picture of inside my head, so it did show I did actually have a brain, which was reassuring for everybody that knew me. Now, I don't want to go into the complex quantum mechanics of NMR, and I'm sorry if there are NMR enthusiasts in the audience who are listening, that this is going to be a real sweep through very quickly. But basically, what we measure is the difference between two nuclear spin states, in this case, hydrogen. They're like little bar magnets, and we put energy into that system, and it flips these spins between these states. And it's that response to energy going in that we measure as an NMR signal. So it's all to do with energy levels. We have the energy level in the system and the energy level in the outside world, and they talk to one another. And this transfer of energy between these systems is relaxation. Now, there's two types of this relaxation behavior. There's relaxation in the spin system itself, and that's an internal transition, and we call that the spin-spin relaxation. Then there's the interaction of the spin system with the outside world. So, for example, if you have a rotating molecule, the molecule is rotating as a certain rotational energy, and those rotational energy levels couple to the magnetic energy levels in the nucleus, and they talk to one another. And that's a way of using the NMR signal to tell you how molecules are moving. So NMR is really about relaxation. And as the nuclear spin precesses around its z-axis, as you can see in this little figure here, we learn about the structure and the dynamics of the spin system. Now, in order to relate a measured relaxation time to how things move, it's a little bit complicated. And one way of visualizing this is to understand the concept of the correlation time. And this funny little video is meant to show you this. So this is a football, and this is a little bit like Luton Town, if ever you've seen them play. Someone kicks the ball to begin with, and after someone's kicked it, they know exactly where it is. It's just in front of them. But after it's been passed to lots of other players, right down the other end of the field, then there's no correlation. There's no information about where the ball was compared to where the ball is. So there's a loss of information. And this time it takes for the ball to forget where it came from is called the correlation time. And it depends on the motion. Now, this is a haphazard motion we can see here. But in a rotation, the information is more coherent and it comes in and out of phase as the molecule rotates. So the rotation can be coupled to this number, the correlation time. And I'm sorry this is a complicated picture, but I just want you to look at two things. On the bottom, we have this correlation time. Liquids have very fast correlation times because the molecules are moving fast. Solids have very, very long correlation times. In fact, the molecules may not even move at all. And on the other axis, on the y-axis, we have the relaxation time. And if you see the red line, you can see that as the molecules are moving faster, the relaxation time changes. Okay, and one of these is the T1 relaxation time, and the other one is the T2 relaxation time. So we've got fast motion on the left, slow motion on the right. So solids have short relaxation times, and liquids have long relaxation times in terms of T2. T1 is a little bit more complicated. In the liquid range, T1 and T2, for an ideal isotropic atomic liquid, they're exactly the same. So for water, for example, T1 and T2 are virtually the same number. But as you go into the solid phase, you can see they diverge and T1 becomes long again, T2 becomes short. Now, you don't have to remember all this, but just if you get the general idea that measuring the relaxation time tells us about mobility. And short relaxation times are solids and long relaxation times are liquids. And this is just some data that we measured a long time ago from different types of material. So for example, on the left-hand side, we have a resin. This is a polyhedral silica resin, silicon-based resin. It's a solid and it has a very short relaxation time, as you can see by this curve falling very rapidly and coming to zero after a millisecond. On the other side, we have an atomic liquid, a molecular liquid. It's 3 angstroms. It's small, it's a liquid, it's pourable, and you can see the relaxation time here is dead well after a second. And then in the middle, we have a medium-sized molecule. It's a polymer, a liquid polymer, and this has a relaxation time intermediate between the solids and the liquids. So by measuring the T2 relaxation time, and that's really what I'm going to emphasize in my talk today, and as will David tomorrow, is a direct measure of molecular mobility. Now, the other little thing we do in our experiments, because most of the experiments are concerned with dispersions, is what can we learn about the structure of a dispersion by measuring the mobility of the liquid it's dispersed in. So these are meant to be silica particles. And around the surface of the silica particle are absorbed water molecules. And the ones between the particles are liquid, free water molecules. So the free water molecules have a long relaxation time. They're just like normal liquid. But the water molecules that are at the interface are trapped. They move with the particle. So in fact, they look more like a solid because they're trapped, attached to the particle. But what happens is this is a very dynamic system, and any of the molecules that are on the surface can exchange with any of the ones in the bulk. And you can see the different colors corresponding to ones that are exchanging, going backwards and forwards. All the blue and dark blue water molecules are exactly the same, but they're in this dynamic equilibrium between each other. That means if you measure the relaxation time of a bulk water molecule, it's an average, it's a dynamic average of what happens at the interface and what happens in the bulk solution. And if those of you like equations, here's an equation which tells you the average relaxation time. This is actually the relaxation rate. It's 1 over the relaxation time. Depends on the number of free water molecules and the number of bound water molecules. And so by measuring this number, the first thing we can tell you is how many bound water molecules there are. That is directly proportional to the available surface area of the particles. So immediately we have a very simple way of measuring the available surface area, or the weighted surface area, in a dispersion. And this is the key to virtually all the experiments that we're going to show you today. Okay, a little bit about the hardware. This thing is called a red pitaya. It's a software-defined radio, and it's basically a programmable chip with a lot of hardware, radio frequency hardware built into it. And so when you buy one of these off the shelf, you can make it into an oscilloscope. You can make it into a radio transmitter receiver if you want to set up your own radio station. We've reprogrammed the internal logic here, the FPGA in the middle of this thing, in order to do NMR experiments. And it's very, 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 very flexible. So the radio frequency range is 0 to 50 megahertz. Our current machine works at 13 megahertz for protons. But if you want to use fluorine or deuterium or lithium, then they're lower frequencies, and we can go right through that whole range. Hydrogen has the highest frequency. It's got digital inputs and outputs. It's Wi-Fi enabled, and we've programmed it to run with MATLAB. It's a commercial piece of software that you write your own operating system in. The hard work is actually done in C because that needs to be fast. So at the moment, we're just using the MATLAB software. We have another project ongoing using Python. And in case at some point, some people might like to write their own code to run the machine, that will also be available. Okay, this is what the machine looks like. It's a little box like this. It's in 2 bits. This is the controller box, which contains the power amplifier, the red pitaya, the power supplies. And then there's the pod, which contains the magnet, and the sample just goes in the top. Now, the pod can always be at any distance from the box. Typically, we'd have it next to it, but you could have it up to 20 or 30 meters away if you wanted to. So you could have a remote sensing NMR machine. And this is what the basic software looks like. We've tried to write it so that it's relatively easy to use. So you have these different buttons for doing things: home, standard, sample details, run options, print, save. You can do all the sort of things you would do in a normal experiment. So the T2 measurement, I just had this little video to show you how the T2 experiment works. I'm not really going to explain this, but you'll see it's quite a complicated business. So the spins precess and rotate around the XY frame. And what we see on the oscilloscope is a series of these called echoes, spin echoes. And when we have all the echo train complete, we take the heights of the echoes and we use those to get the NMR relaxation time. I mean, I haven't really explained that, but just to give you the idea, it involves, in general, if we're looking, say, at water, which has a T2 about 2 seconds, we'll probably generate something like 16,000 of these pulses. And we take the height from each of them, so we get a representation of the system. So a little bit more about water mobility. This is just a video that one of my PhD students created quite a few years ago. It's a beautiful demonstration. I'll just show you this. So this shows what happens to a water molecule where it's near an interface. This is a water droplet. And if I can make this video work. So you can see the water, once it reaches the interface, it gets into the gaps and the holes, and the water molecules become trapped. So their mobility of ones that are in the bottom of one of these little crevices is highly restricted compared to the water molecule on the top. So you may be able to see one other application of this straight away is that we can look at mobility in pores. In fact, we can look at pore structure in materials. Okay, so a little bit about how to estimate surface area. Now, you do need to calibrate this because the absolute values of the relaxation lines for bulk water are known, but for the surface water, it's not known. So you have to basically have a handle on what that number is. But if you know that, we can encapsulate the unknown parameters in what we've called the Ka parameter. So the actual specific surface area, if you've calibrated with Ka, depends on the volume fraction, volume ratio of particles to solvent, and then the relaxation times that you measure, R2SP, and the relaxation time of bulk water. So you can see it's a very, very simple formula. Once you know this calibration, you can get the surface area. Now, if you don't know the calibration constant, you can still produce a parameter which is proportional to the surface area. And in many cases, that's very useful in its own right. So this is a video of how the machine works, and hopefully this will work. So this is if you have a silica dispersion and you know this unknown parameter and you want to measure surface area. So the experiment is in two parts. First, we run a background to make sure the machine is on resonance, and you'll see a line going from the bottom left-hand side to the top right-hand side of the diagram, and then you'll see a wait while we get the experimental data. Hopefully this will work. Oh, sorry. Okay, so the first thing that happens is we go on the sample details and we set some parameters. We say this is going to be silica and water. We put in the concentration, 5%. We go to run options and we choose T2. And we want to measure surface area, so we click that and then we press the start button. So the first thing we do is the machine goes on resonance. You can see that's relatively quick. And then we have to wait to get the experimental data. Now this is a silica dispersion with a relaxation time of the order of 200 or 300 minutes. There, it's done it. So you can see we get a curve, and directly from that we can get the surface area from this calibrated sample. It's 121 meters squared per gram. So you can see it's a very rapid, straightforward experiment. You can do this with settling. You can do this by adding additives. Because it's so fast, you can actually do experiments in the NMR tube and get online data. So these are some not so recent data, but still nice data, looking at different particles and seeing how they affect the NMR relaxation time. So silica is one of the samples we've studied mostly. If you plot the R2SP against the surface area, we get a nice straight line. If you do it for alumina, now alumina obviously has aluminium atoms in the interface, and these interact differently with water magnetically. And so the effect for alumina is stronger than it is for silica. Polystyrene latex is basically a hydrophobic surface. So the interaction of water with a hydrophobic surface, well, partly hydrophobic surface, it does have sulfonate groups on, is much weaker. So you can see the slope of these curves tell us something about the surface energy, the interaction between the water and the interface. The sort of thing would be very hard to, without doing a complicated calorimetry experiment, to get some idea of that sort of interaction. It's quite difficult. And these experiments, they take minutes to do. So this is a nice application. Well, in fact, this is how I started on this in the first place, is we were measuring absorption isotherms of polymers onto particles. And it's a very tedious experience. And I think there might be one of my PhD students in the audience here who's suffered through this. Kathy, hello, I think you're there. And these are some of her data, certainly the data I showed earlier. So if you want to measure the absorption isotherm, you basically take your particles, you add polymer, you measure the depletion of polymer from the bulk solution, and that gives you your adsorbed amount. It's a terribly tedious and awfully boring experiment. Now, with the NMR experiment, all you do is you put your silica, say, sample in the NMR tube, measure the relaxation time, you add 1 milligram of polymer, measure it again, 2 milligrams of polymer. So you can get one of these absorption isotherms probably within half an hour once you know what you're doing. So this is terrific because you can now see, for example, PEO, PVP absorption. The PVP is much more strongly absorbed than PEO. In fact, from these experiments, we can actually do a clever experiment. We can absorb PEO onto a surface, then add PVP, polyvinyl pyrrolidone, and it displaces it. Now that's a very useful thing in a complicated dispersion, because if you're stabilizing a particle, you want to know that the stabilizing polymer stays on the surface. You can also challenge an adsorb layer with different things. This is this is a very complicated diagram, but this shows looking at first PEO adsorption and then adding PVP and seeing the displacement of PO and PVP. And at some points, obviously, both polymers can be absorbed. There's a reference here, and I think Keith will make this presentation available to anybody who wants to look at this in detail afterwards. But I think you can see the power of a very simple experiment that takes minutes to do, and we can get detailed information about polymer absorption. This is another nice experiment. This is many formulations are complicated. You might have particles, polymers, surfactants, proteins, goodness knows what in a complicated mixture. Can you work out what happens at the interface? Well, one thing that is well known is that polyethylene oxide strongly interacts with sodium dodecyl sulfate to make a polymer surfactant pair. So if you absorb polyethylene oxide onto silica and then you add SDS, you can see from our graph that the addition of the SDS causes the polymer to completely desorb. So this is the bare silica value. This is the value with PEO, and just titrating at SDS makes it desorb. Now, one interesting thing you can do with this is that you can work out the strength of the polymer surface interaction from the concentration of surfactant needed to desorb it. So it's like doing a calorimetry experiment, but getting an actual number from the absorption energy Another thing that we've been looking at more recently is whether or not you can measure porosity. Now, a pore is a rather different object to the outside of a silica particle. But if you think of a pore like the picture I've drawn here, we have water confined in the pore, so there's adsorbed water on the internal interface, and that's in bulk in exchange with water in the center of the pore. So the average relaxation time, again, tells us something about the surface area inside the pore. Well, of course, the surface area inside the pore, we can directly relate that to a radius. So that means that we can get the radius of a pore directly from the relaxation time. And in a complicated system with complicated shaped pores, channels, connected pores, disconnected pores, we can dig into the internal structure a little bit as mercury porosimetry does, but with a much simpler and a much safer experiment. So this is just some simulation data. So this is a system where you've got pore water and bulk water, and this is the water in the pore, this is the bulk water, and this is the combined result. And if you then try and fit that data, so you do the NMR experiment, that's the green dots, and you try and fit it to a single or a double exponential, then you can learn about the two different environments, the bulk water and the surface water. You can do much better than that. And in fact, some of you who are familiar with light scattering will know about the content analysis used in DLS for deconvoluting multiple correlation functions. Well, it turns out you can use exactly the same analysis procedure with NMR relaxation times. So in a typical NMR experiment, we might have 16,000 data points. So you can see that it makes this type of deconvolution really useful. In DLS, of course, you never get that number of data points. And so we can use the content analysis and dig out. So this is synthetic data. It's from 3 different pore sizes. And you can see we get 3 different peaks in the relaxation time distribution. This is still in time, but you can convert this axis directly to size, again, if you know the Ka parameter. In the last part of the talk, I want to talk to you about another experiment you can do with our apparatus. You can measure self-diffusion. Now, this looks horrendously complicated, I know, but any of you who are interested in NMR, you can generate these really complicated pulse sequences. These are RF pulses, and these are gradient pulses, the same pulses that any of you have had an MRI will know. They sound like loud clicks in your ear, and in fact, if you listen to our machine, it clicks away quite happily. And in between here, we do a rather complicated NMR experiment. But at the end, we have a signal that we can measure. And this is a graphics of this experiment. We switch on the field gradient, and instantly the signal seems to disappear. But it's now diffusing through space. So if we like, we took a snapshot of where the molecules were. Then a little later, we take another snapshot, and we compare those 2 snapshots. And from those 2 pictures, we can work out how each of the molecules has moved. I mean, It sounds almost unbelievable, really. You're tracing the path of single molecules through space. And it's because each of those molecules has a signature. It's in a known value of magnetic field, which means it has a known precession rate, if those of you understand that stuff. So it's like taking a photograph of where all the molecules are. Oops, I started it again. Never mind. It's quite pretty. We can watch it again. So at this point, we take a photograph of where all the molecules are and pretend they're all different colors. And then a little later, we take another photograph. And we compare those two photographs. And we see that a blue molecule has moved to a different place. A red molecule has moved to a different place. And so we can map out the trajectories of all those different molecules over this time regime. Now, this time regime is something like 10 milliseconds to 10 seconds. It depends on the sample, but allows us to measure self-diffusion. And this is also a really powerful tool. So this is some experiments on water. Right? And what we're doing in this experiment is measuring the signal height. Oops, sorry. The signal height as a function of this parameter here. So the time constant of this curve is the diffusion coefficient. And what we're doing here is taking the diffusion curve from here and looking at how it varies with time. Now, water, in bulk water, the diffusion coefficient is independent of time. Eventually, it'll hit the side of the tube and bounce back again. But we're looking at distance scales between 100 nanometers and about 100 microns. That's how far we can follow the trajectory of a molecule. And you can see for that my water sample that it's independent, as you'd expect. Now think about water inside a pore. Water inside a pore can only traverse the diameter of the pore. So again, from the diffusion coefficient, we can measure the internal diameter of the pore. And that also gives us a handle on calculating this Ka parameter I mentioned before. So combining the diffusion experiment and the relaxation experiment, we have an absolute method for measuring surface area. So just some other things. Okay, you might be interested in different liquids. So this is water. And again, I say the time constant, well, it's a Gaussian function in this case, but the time constant for water tells you that the diffusion coefficient is a large number. If we go to octanol, a much bigger molecule, it's slower. And if we go to a polymer liquid, it's slower still. And so we can measure the diffusion coefficients of bulk liquids and solvents, molecules, polymer solutions, gels, and they all have very valuable structural information. This is just some test experiments we did when we were putting the machine together. So this is the diffusion coefficient of alcohols as a function of molecular weight and paraffins. And you get a nice straight line using a power law. And the exponent of this is -2. For spherical molecules like polymers, it would go as -1. For polymers, it goes as -2, depending on molecular weight, up to -3. So this is a tool for looking at basic materials. Okay, well, I've gone through, hopefully not too quickly through my presentation, but just to go through again, what can you measure and what can't you measure? So the relaxation number, the relaxation time, allows us to look at liquids, suspensions, emulsions. It's broader than that. We can look at cheese, we can look at blood, we can look at tissues, you know, almost anything, like I said before, that you can get inside the NMR tube, you can learn about this internal structure, and in particular about the mobility of the molecules in that situation. You can measure flow, for example. So if you could get, this is how you can measure how MRI works, to measure the blood flow through arteries. And we could do the same thing, although we'd have to chop an artery up and get it inside the NMR tube to do it. But in principle, that's something you can do. We can measure the dispersed wetted area of a surface or a suspension. And as I hope I've shown you, that's an extremely powerful tool for investigating issues in dispersions. There are loads of examples of this, and Dave Fairhurst tomorrow will show you some real life examples. But it is a really useful tool if you want to find the best surfactant, for example, to disperse a particle in. If you want to find the best polymer, you want to find out what happens to a polymer dispersion, a tin of paint, for example. If you leave it on the shelf for hours and hours and it settles or flocculates, or, you know, you can learn about all those issues very easily with this technique. You can measure the concentration of particles. Most of you would know that. We can directly measure particle size in a small number of situations for very small nanoparticles. We have a handle on porosity. We can look at porous liquids, porous solids. We can follow dynamics of process because the experiment is relatively rapid. We can look at settling relatively slow. We can look at the dynamics of absorption, the dynamics of competitive absorption, a whole range of very easy experiments, or experiments that are actually quite difficult to do without much more sophisticated experiments. I mean, like neutron scattering or something, you know, beyond most people's means. We can look at impurities, especially ferromagnetic impurities in water. So, you know, in the water industry, using this to detect certain types of elements would be very useful. We can look at oxides. We can look at the oxygen content of solvents. The list goes on and on and on. And we're happy to help anyone who has a formulation problem or a material science problem and thinks NMR can be a useful technique. We're happy to talk to you about it. And I just mentioned briefly the new diffusometer that we've built. We can look at polymer and solvent diffusion. We can measure the molecular weight of polymers in the same way as you do with light scattering. And it's a calibration tool for porosity and a lot of other experiments. And just a few more things about diffusion. So polymer and solvent diffusion. Droplet size of emulsions is something we can do. I didn't really tell you much about that, but in the same way that you can measure the internal diameter of a pore, you can measure the internal diameter of an emulsion droplet. We can look at transfer through membranes, percolation. I've mentioned a lot of things, and you can see it's a very versatile piece of equipment. So these are two things that you might be interested in. So Roger Petman, as I mentioned before, is our worldwide CEO and in charge of all aspects of the company, sales, marketing, and so on. And in Europe, Keith Sanderson, who's hosting this webinar. Keith, I think I've come to the end. I've probably gone a bit too fast. I think hopefully we've recorded this. So if anyone would like a copy of the recording or the presentation, I'm very happy to provide that. And I'm very happy to answer questions live now, or if you want to send them in, we're happy to look at them as well. If you have interesting samples you think NMR might be useful for, you'd like us to measure them, again, we'd be happy to do that.